As soon as we say a system, it's all about feedbacks, right? So we have to also worry about the feedbacks between the climate impacts and then the forcings themselves. So there is anthropogenic forcing, which is creating climate change, which is having an impact, but then the impacts feed back onto the forcing itself. Okay, so this is showing that cartoon in terms of the nexus between energy, water, and food, feed, fiber, and climate change. So nationally appropriate low meat diet or low water consuming vegetarian diet generally reduces water and energy demand as well as greenhouse gas emissions per capita, of course. Use of agricultural, livestock, and food waste may reduce conventional energy use and greenhouse gases. Climate change tends to increase energy demand for cooling as well as water demand. So you can see how food, water, and energy use and climate change are related to each other here. The broader example here is to look at water, energy, food, feed, fiber. Usually it's just referred to as FUES, food, water, or food, energy, water nexus. Honestly, I think we should add health to this as well. So they are obviously starting with greenhouse gas emissions and climate change. But if you look at in each sector, you have water for energy, like cooling for thermal power plants, hydropower, irrigation of bioenergy crops, extraction and refining of fossil fuels themselves, fracking, for example, and energy for water, so extraction and transportation of water, water treatment and desalination. Desalination is becoming now more and more. Wastewater, drainage treatment, and disposal. Sorry. On this side you have water for food, feed, and fiber, so irrigation, livestock, water used for food processing, and impact of food, feed, fiber production on water quality and runoff generation. So pesticide use, for example, heavily affects not just water quantity but also water quality, and that goes into coastal waters, groundwater, and so on. On the energy side, you have energy for food, feed, and fiber, and you also have food, feed, and fiber for energy production when especially do bioenergy. And the RCP 2.5 actually relies heavily on what's called BECCS, bioenergy and carbon capture and sequestration, as part of the solution to staying below 2 degrees centigrade global warming, or keeping the radiative forcing to 2.6. Okay, watts per meter squared in terms of imbalance. So that's something that will affect the nexus between food, water, and energy. So there is competition between bioenergy and food production for water and land, and social scientists also worry about its impact on food security, food prices, and so on. There is other effect that has been noted already for a while, and that is the CO2 fertilization impact on evapotranspiration and runoff. So in a simple sense, the leaves have to open, the stomata opens to capture CO2 from the atmosphere. It has laboriously moved water and nutrients up from the roots through capillary effects all the way to the leaves to do photosynthesis. So the goal is to open the stomata long enough to capture enough CO2 but not lose much water. So that stomatal conductance is going to be affected if CO2 in the atmosphere increases. And there is some evidence that the water loss is reduced, so the infiltration and or the exudation of water from the roots is increasing, and maybe increasing surface runoff. Obviously, more data is needed, but the processes involved here are, of course, with land use change being interacting with CO2 fertilization, is the processes of infiltration, subsurface runoff, and surface runoff. So CO2 also affects directly the physiological forcing of transpiration and surface evaporation. So it's more and more obvious that, remember that difference in water vapor pressure between in the leaf and the atmosphere matters. So with the warming, the vapor pressure deficit is also a very critical factor. So all these three processes are affected by climate change, and transpiration is additionally affected by changes in vegetation water use efficiency, which is related to atmospheric CO2 concentrations. So obviously, to resolve these, you need Earth system models. We touched already upon these online offline model calculations. This is an example of changes in runoff by the end of the 21st century, simulated by HAD-CM3 model from the UK. Directly, which means the hydrological land model was part of the Earth system model. And in B, the MACDPM is their land model is run offline, driven by meteorological output. Okay, I removed C from here, the differences between them, but you can already see the huge differences between them. The stipples here show where the two approaches agree on the sign of the runoff change. So there are many places where there is no confidence and the models actually don't even agree on the sign of the change by the 21st century. So just to repeat, the offline calculations, which are very fast because you just take the model output and you run the hydrologic model, they can help a lot with short-term water resource management and so on. But when you do longer-term projections, they do not do water balance, so it can be a problem. So we have to be aware of the online versus offline calculations. Just like IAMs, the integrated assessment models are offline models in the sense they take the climate forcing from the Earth system models. So you can do an iteration like we showed for producing RCP scenarios, but that is still not the same as having nested feedbacks. Okay, I hope that's clear.